Hi friends, in this video we are studying turbo machinery subject, impulse turbine. These are steam impulse turbine, chapter objective questions and answers. This is a picture of an turbine with multiple stages. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are 12 stages. And here we have nozzles. That part is removed. From the nozzle, steam enters. So this is the rotating part. And in middle we have stationary part. And then second stage. And then again we have stationary part in middle that is not shown in the picture. So this is the turbine picture. A turbine is called as impulse turbine if at the inlet of the turbine total energy is only kinetic energy, total energy is only pressure energy, total energy is sum of kinetic energy and pressure energy, none of the above. So the question is about impulse turbine inlet, which type of energy is given out of these options. So we have Bernoulli's principle. There are three types of energy: kinetic energy, half rho v square or half mv square, and work done by weight, also called potential energy, that is rho g z or rho g h. Z is height, g is gravitational force, rho is density, and then work done by pressure, that is also called pressure energy. So here in question we have to answer which of the form out of these three is given as the input of the impulse turbine. So when we see the pressure and velocity diagram of an impulse turbine, at the nozzle the steam enters with high pressure and low velocity. This high pressure is decreasing at the entry of nozzle and velocity is increasing. So here pressure got decreased and the velocity got increased. That means we are converting pressure energy into kinetic energy at the nozzle. So the question is inlet of the turbine. So inlet of the turbine is from moving blades. So inlet of the turbine, there is high velocity. So we are converting pressure energy into kinetic energy. So therefore inlet of the turbine, we are giving the kinetic energy. So therefore option A, total energy is only kinetic energy, is the correct option. In an impulse turbine, the steam is expanded in nozzle only and there is pressure drop and heat drop. The steam is expanded both in fixed and moving blades continuously. The steam is expanded in moving blades only. The pressure and temperature of steam remain constant. So when we see the pressure and velocity compounding of an impulse turbine, we know that high pressure to low pressure in the velocity compounding as well as to in pressure compounding, the high pressure is converted into low pressure in the pressure compounding also. So thereby we can answer that the steam is expanded in nozzle only. So from the nozzle, steam is expanded and there is pressure drop and heat drop and pressure drop and heat drop. So therefore option A is correct option. Blade efficiency of an impulse turbine is defined as the ratio of, so they are asking for blade efficiency, nu B. So nu B, the given options are work done on blades, work done on blades. First option is work done on blades per unit mass of steam and energy supplied per unit mass of steam. Work done upon energy supplied. And second option is relative velocity at outlet, relative velocity VR2 at outlet and relative velocity at inlet VR1. And third option is absolute velocity at inlet, absolute velocity V1 and absolute velocity at outlet, absolute velocity at outlet. And fourth option or D option is energy supplied per unit mass of steam. So they are giving energy supplied to the work done on blades per unit mass of steam. Energy divided by work done. So when we see the blade of an impulse turbine, the efficiency of blade is how efficiently blade converts input kinetic energy supplied to the work is blade efficiency. So at inlet we have high velocity jet of steam. So that is kinetic energy is given at the inlet and it is converting it into work by rotating the blades efficiently. So kinetic energy is inlet, work done is outlet. So blade efficiency we can write as work done upon kinetic energy supplied. So therefore option A is work done on blades per unit mass, work done on blades per unit mass. So work done is m dot VW into U and kinetic energy is half mv square. This is v square, that is v1 square. So this is the work done on blades per unit mass and energy supplied, that is kinetic energy supplied per unit mass of steam. So therefore option A is correct option. We have still lot of things to know about blade efficiency. So this is the combined velocity triangle of the impulse turbine where VW is tangential or wheel component of absolute velocity, that is here for inlet and for outlet, and V is absolute velocity, V1 for inlet and V2 for outlet, and U is mean blade speed. So this is U. So the tangential force, the force what it act here, this force is written as Fu is equal to m dot, that is mass flow rate kg per second, Vw1 tangential velocity at inlet minus Vw2, that is m into delta Vw. So force is the tangential force what it acting, that is Fu is equal to m dot into delta VW. So this force is converted into power. We know force in Newton, force into velocity, Newton meter per second, that is watt. So power developed, we are multiplying with U, that is blade velocity into delta W. So that gives the power developed. So blade efficiency is written as work done m dot u into delta VW divided by kinetic energy supplied. The kinetic energy at high velocity supplied. So kinetic energy supplied. So here kinetic energy supplied is m dot v1 square by 2. So that we can write 2u, because this 2 is shifting here, 2u delta vw upon v1 square. So this is the expression for blade efficiency. So blade efficiency is also called diagram efficiency or utilization factor. So these are one another same. Blade efficiency, diagram efficiency, and utilization factor. The stage efficiency of an impulse turbine is defined as the ratio of work done on blades per unit mass of steam and the energy supplied per unit mass of steam. That is work done by energy supplied. Work done by the rotor divided by total available energy in the passing steam. Third option is absolute velocity at inlet and absolute velocity at outlet. Energy supplied per unit mass of steam and work done on blades per unit mass of steam. So here the question is about stage efficiency, that is nu S. So stage efficiency is defined as the sum of work done by the rotor divided by total available energy in the passing steam. So how much work done by this rotor? Work done by the rotor divided by total available energy. That is also called isentropic energy. So total available energy for the rotor to produce work. So that is work done by the rotor divided by isentropic enthalpy drop. So that we can write m dot u into delta VW work done by the rotor and isentropic enthalpy dot drop m dot delta H isentropic. So here we can multiply with the kinetic energy supplied. This is the factor of kinetic energy and this is also kinetic energy. So that gives blade efficiency and nozzle efficiency. So stage efficiency is work done by the rotor to the isentropic enthalpy drop. So that is option B, work done by the rotor divided by total available energy. So here total available energy is nothing but isentropic enthalpy drop. So therefore option B is correct option. The nozzle efficiency of an impulse turbine is 0.8. So they had given nozzle efficiency is equal to 0.8, that is 80%, you may say. And the mean blade velocity is 224 meter per second. Blade velocity u is equal to 224 meter per second. If the velocity ratio of the turbine is 0.7, velocity ratio u by v1. So in any case, if they ask it as a velocity ratio, that is nothing but u by v1. Then the isentropic enthalpy drop in the nozzle is. So they are telling to find the isentropic enthalpy drop. that is delta H isentropic. So we know nozzle efficiency is equal to kinetic energy input. So m dot we write here and m dot. So this m dot and m dot cancels. So kinetic energy input divided by isentropic enthalpy. So we have U equal to 224 meter per second. And velocity ratio is also given. U by V1 is equal to 0.7. So V1 will be 320 meter per second because as U is 224 and it will be 320 meter per second. So nozzle efficiency becomes V1 square by 2 and delta H isentropic. So let's put the value. V1 is 320 square, 2 is here into 0.8. So that gives 64,000 joule per kg. So that is equal to 64 kilojoules per kg. So thereby option A is correct option. For an impulse turbine, the nozzle efficiency is 90%. The blade velocity ratio is 0.5 and mean blade velocity is 150 meter per second. This corresponds heat drop in the nozzle is equal to. So here they are asking about heat drop and the given options are in kilojoules per kg. So that means they are asking about the enthalpy. So we know the given here are nozzle efficiency is equal to 0.9. So nozzle efficiency we know m dot v1 square by 2 upon m dot delta H isentropic. So here m dot get cancels. So that is equal to 0.9. And blade velocity ratio is given 0.5. That is u by v1 equal to 0.5. So v1 equal to 2u, that equal to 300 meter per second because u is given already. U is 150 meter per second. So that gives v1 equal to 300 meter per second. And kinetic energy or theoretical enthalpy. So this part is also called as theoretical enthalpy or also kinetic energy. And this is isentropic enthalpy or also it is called delta H actual enthalpy. So theoretical enthalpy is V1 square by 2, that is 300 square by 2, 45,000. So that will be 45 kilojoules. So we will put it in the nozzle efficiency equation. 0.9 equal to V1 square by 2 delta H isentropic. So that is 45 upon delta H isentropic. So we get delta H isentropic as 50 kilojoules per kg. So thereby option B is correct option. Maximum efficiency in impulse steam turbine is 2 cos alpha, cos 2 alpha, cos alpha by 2, cos square alpha, where alpha is nozzle angle. So the question is, what is the maximum efficiency for a given nozzle angle? So we have the graph of blade efficiency versus velocity ratio u by v1. So when we plot this graph for cos square alpha 1 for impulse turbine, the efficiency is maximum. And for reaction turbine, 2 cos square alpha upon 1 plus cos square alpha, the efficiency is maximum for the reaction turbine. So therefore option D, cos square alpha is the correct option. Assertion: a convergent divergent nozzle is used to deliver stream to the turbine or blades at high pressure. So let's see what is convergent divergent nozzle. So this is the convergent divergent nozzle. Here this is the convergent section where it is converged, and this is the divergent section where it has diverged. And the question assertion is convergent divergent nozzle is used to deliver the stream to the turbine or blades at high pressure, but it is not used to deliver the stream at high pressure. The pressure output here is low pressure because at inlet it is high pressure and low velocity, and this will be converted into low pressure and high velocity. So that is kinetic energy, half mv square. So thereby assertion A is wrong. And reason R is a stream nozzle is a passage of varying cross-sectional area in which the energy of steam is converted into kinetic energy. Yes, the high pressure and low velocity steam enters and it will be converted into kinetic energy, that is low pressure and high velocity. So that gives reason R is correct. So this confirms assertion A is wrong, reason R is correct. So as per given options, both A and R are individually true, that is wrong. Second option, A and R are individually true, that is also wrong. A is true but R is false, that is also wrong. And A is false, that is correct, and R is true. So option D is correct option. In a convergent divergent nozzle, normal shock generally occur. So they are asking about the where does the shock occur in the convergent divergent nozzle. So given options are along the divergent portion of and throat, along the convergent portion, anywhere along the length, near the inlet. So when we see the convergent divergent nozzle, the shocks are likely to occur in the throat and divergent portion, in this portion, because stream enters at high pressure and low velocity and gets exit with low pressure and high velocity. This steam or stream will observe the shock at throat and divergent section. So this is somewhere here. So that gives option A along the divergent portion and throat. That is correct option. Consider the following statements. Almost all flow losses take place in the divergent part of nozzle. So when we see the nozzle, this is the nozzle. So the statement 1 is almost all flow losses take place in the diverging part of the nozzle. So this is the diverging part. So almost all flow losses are take place in here. So that is statement 1 is correct. Normal shocks are likely to occur in converging part of nozzle. So they are telling in the converging part the shocks will occur. That is false. The shocks will occur at throat and diverging part. So therefore statement B is wrong. Third statement is efficiency of reaction turbine is higher than that of impulse turbine. So we can see here reaction turbine efficiency and impulse turbine efficiency. Reaction turbine has high efficiency compared to impulse turbine. So that means statement 3 is correct. So this concludes 1 and 3 are correct statements. That is option D is correct option. Which of the following statements are true? In impulse turbine, steam expand in nozzle and remain in constant pressure while passing over blades. The statement 1 is about impulse turbine. So when we see the velocity compounding of impulse turbine, as per the statement, steam expand in nozzle and remain in constant pressure while passing over the blades. The steam will expand in the nozzle, this is the nozzle, and remain in constant pressure, that you can see here. It remain in constant pressure while moving over the blades. So that gives statement 1 is correct. And then when you see it for the pressure compounding, it is same. Steam expand in the nozzle and remain in constant pressure while passing over the moving blades. This is constant pressure in the moving blades. So statement 1 is correct. Statement 2 is, in impulse turbine, steam expand in nozzle and pressure change while passing over the blades. So they are telling, while passing over the blades, the pressure will change, but the pressure will remain constant while passing over the blades. So that gives statement 2 is wrong. And third statement is, in reaction turbine, steam constantly expands as it flows over the blades. So when we see the pressure compounding of reaction turbine, the steam is constantly expands as it flows over the blades. So that is correct statement. So that gives statement 1 and 3 are correct. So option B is correct option. Steam at exit from nozzle of impulse turbine has low pressure, high velocity, high pressure and low velocity, high pressure and high velocity, low pressure and low velocity. So here the question is about steam exit from the nozzle. Sorry, steam exit from the nozzle is here because nozzle is here. So when we see the velocity compounding of impulse turbine, steam exits from nozzle, and pressure compounding of impulse turbine, steam exits from nozzle. So the first option is low pressure and high velocity. The pressure is high at the nozzle entry and pressure is low at the nozzle exit. So for velocity compounding, it is true. For pressure compounding, high pressure at nozzle entry and low pressure at nozzle exit. So that means option A is correct option. Thank you for watching video. If you have any doubts, please comment on the comment box and don't forget to subscribe and like. Thank you.